Hello and welcome students to Make Pro Classes, my official YouTube channel. Myself Piraj Mojumdar, Assistant Professor of Mechanical Engineering Department, GKCM, that is Greater Kolkata College of Engineering and Management under JIS Group. Welcome you to our new session of Advanced Welding Technology, where we will be uploading all the lecture series according to MacOut syllabus day by day. So keep in touch with us for getting daily updates. You can also contact me through 9433465217, that is my personal phone number, or even you can email me at pirasar@gmail.com. You can also connect me through social networking, that is Facebook page, which is known as Make Pro Classes. So let us start today's online session. So you have completed so far the welding metallurgy and has. Now today we will be discussing on effects of different process parameters on the characteristics of weldment. So let us begin our today's class. So here we will discuss the different parameters that affecting the welding. So in this study, the effect of various welding parameters on the welding of mild steel specimens having dimensions 50 mm into 40 mm into 6 mm welded by metal arc welding were investigated. The welding current, arc voltage, welding speed, heat input rate are chosen as this welding parameters. The depth of penetrations were measured for each specimen after the welding operation on closed butt joint, and the effects of welding speed and heat input rate parameters on depth of penetration were investigated. Welding technology has obtained access virtually to every branch of manufacturing. To name a few: ships, rails, road equipments, building, constructions, boilers, launch vehicles, pipelines, nuclear power plants, aircrafts, automobiles, pipelines, etc. Now, welding technology needs constant upgrading, and with the widespread applications of welding, to consistently produce high quality of welds, arc welding requires experienced welding personnel. One reason for this is the need to properly select welding parameters for a given task to provide a good weld quality, which identified by its microstructure and the amount of spatter, and relied on the correct bit geometry. Therefore, the use of control system in arc welding can eliminate much of the guesswork often employed by welders to specify welding parameters for a given task. Investigation into the relationship between welding process parameters and bit geometry began in the mid 1900s, and regression analysis was applied to geometry research by Lee and Ravindra. Many efforts have been carried out for the development of various algorithms in the modeling of arc welding process. In the early days, arc welding was carried out manually so that the weld quality can be totally controlled by the welder rapidly. Now, McGlone and Chadwick have reported a mathematical analysis correlating process variables and bit geometry for the submerged arc welding, square edge, closed butts. Similar mathematical relationship between welding variables and fillet weld geometry for gas metal arc welding using flux cord wires have also been reported. Chandel first applied this technique to the GMA welding process and investigated relationship between process variables and bit geometry. These results showed that earth current has the greatest influence on bit geometry, and the mathematical models derived from experimental results can be used to predict bit geometry accurately. Nearly 90% of the welding in world is carried out by one or the other arc welding process. Therefore, it is imperative to discuss the effects of welding parameters on the weldability of the materials during the arc welding. Mild steel is the most common form of steel because its price is relatively low, while it provides material properties that are acceptable for many applications. The variables affecting weld quality in arc welding are classified into following groups: welding current, welding voltage, welding speed. Welding current is the most influential variable in arc welding process, which controls the electrode burn off rate, depth of fusion, and geometry of the weld mix. Welding voltage is the electrical potential difference between the tip of the welding wire and the surface of the molten weld pool. It determines the shape of the fusion zone and weld reinforcement. High welding voltage produces wider, flatter, and less deeply penetrating welds than low welding voltages. Depth of penetration is maximum at optimum arc voltage. Now, welding speed of welding is defined as the rate of travel of the electrode along the seam of the on the or the rate of the travel of the work under the electrode along the seam. Some general statements can be made regarding speed of travel. Increasing the speed of travel and maintaining constant arc voltage and current will reduce the width of bead and also increase penetration until as an optimum speed is reached, at which penetration can be a maximum. Increasing the speed beyond this optimum will result in decreasing penetration. In the arc welding process, increasing welding speed causes decrease in heat input per unit length of the weld, decrease in the electrode burn off rate, decrease in the weld reinforcement. If the welding speed increases beyond a certain point, the penetration also will decrease due to the pressure of the large amount of weld pool beneath the electrode, which will cause the arc penetration force. Now, the different parameters they have found out when the welding voltage was 24 and welding current was 25. Welding current was 105 amperes. Arc time was 25.4 second. Welding speed was around 94.48 millimeter per minute, and heat input rate was 1600 joule per millimeter, and penetration was 4.3. Next, they have kept the constant voltage and constant current, but the arc timing was changed to 25 to 23, reducing the arc time and increasing the welding speed, that is from 94 to 101. Heat input rate also decreased to 1490 from 1600, and the penetration also increased from 4.3 to 5.1 millimeter. Now, the effect of welding speed on depth of penetration. Readings of the depth of penetration obtained through measuring instrument after cutting all the welded specimens perpendicular to the direction of welding are analyzed with the help of a graph and is plotted between welding speed and penetration. Voltage 4 volt and current 105 ampere are taken constant, and arc time is varied during the welding of specimens. The depth of penetration increases with increasing welding speed up to 110.39 mm per minute, which was optimum value to obtain maximum penetration, because it begins to decrease linearly after this point. Increasing the speed of travel and maintaining constant arc voltage and current increases penetration until an optimum speed is reached, at which penetration is maximum. Increasing the speed beyond this optimum results in decreased penetration, so it can be concluded from experimental analysis that for the mild steel specimen having dimensions 50 into 40 into 6, optimum weldability can be achieved by considering the welding parameters as welding speed 110 mm per minute with current 105 ampere, arc voltage 24 volt, and electrode diameter 2.5 mm. Now, the effect of heat input on depth of penetration. It is evident that there occurs maximum depth of penetrations at heat input rate of 1369 joule per millimeter. Greater the depth of penetration, better is the weldability. So, optimum weldability can be obtained with the heat input of 1369.68 joule per millimeter. Now, coming to the conclusion. Optimum parameters for the weldability of mild steel specimens of dimension 15 to 40 into 6 when current is 105 ampere, arc voltage is 24 volt, An electrode chosen is E6011, diameter 2.5 millimeter, come out to be when the welding speed was taken as a variable parameter. The deepest penetration, that is 5.41 millimeter, was obtained in 110.39 millimeter per minute. Maximum depth of penetration was obtained when heat input rate was 1369.68 joule per millimeter. Hence, it can be concluded that increasing the speed of travel and maintaining constant arc voltage and current will increase penetration until an optimum speed is reached, at which penetration will be maximum. Increasing the speed beyond this optimum value will result in decreasing penetration. Likewise, there are some also effect of different input parameters on weldment characteristics in tungsten inert gas welding as well. Weldment characteristics like penetration, bead geometry, and depth of haz are extremely important characteristics of structural integrity in the case of welded joints. TIG welding process, which is used throughout the country for its simplicity and versatility, induces various defects like blowholes, porosity, undercut, and irregular as depending on the process parameters used: electrode diameter, current, voltage, arc travel speed, plate conditions like preheating, arc are influential um, factors in deciding weldment characteristics. It is extremely important to model and predict weldment characteristics depending upon the local operating conditions and to optimize them. In this present work, effect of process parameters like current, voltage, electrode diameter, arc travel rate on weldment characteristics in case of TIG were studied. A number of experiments were conducted on a present feed-based TIG machine using all the process parameters described. Weldment characteristics like depth of penetration, depth of haz, number of undercuts, area of penetrations were examined for the weld bits obtained from experiments. The aim of the work is to study the effect of process parameters on weldment characteristics. So, bead geometry. The bead height and the bead width together constitute the bead geometry. The portion of the parent material which has been heated and melted and has the characteristics dendrite structure of a casting is called weld bead. Bead geometry depends on weld process parameters and the workpiece temperature. For example, for some welding process parameters, formation of a bead may be possible in preheated plates, but it may not be possible for workpieces which are in room temperature. Similar phenomena may be observed in case of cryo-treated plates. Now, depth of penetration. It is the depth to which base material and filler material have melted and mixed during welding process. It depends on the weld process parameters used and can vary for different plate conditions. The portion of the parent material which has been heated above the critical temperature but has not melted, that is the depth of haz. Now, the hardness test. Hardness is defined as the resistance of a material to plastic deformation, usually by indentation. It also refers to the stiffness or resistance of welding to resistance to scratching. Indentation hardness refers to number related to the area or depth of the impression made by an indenter of fixed geometry under a non-static load. There are many methods to determine the hardness. Among those, Brinell and Rockwell hardness tests are frequently used. In our testing procedure, first test was hardness test. For hardness test, we made different test specimen. We cut a piece of 10 millimeter from the length of the welded pieces, like we made 50 pieces of weldment for hardness test. Before hardness test, we need to make the smooth surface of piece which we got cut after cutting. For making it smooth, we are using the MRE papers actually of 220, 320, 400, 600 graded papers. we got smoothness required. After getting appropriate smoothness, we have done a hardness test for parent material and welded zone. In hardness test, we found the materials hardness of material after welding got increased. Now, Brinell hardness test, it is the method of obtaining the hardness of material in which indenting the surface of a sample by a steel ball of specified diameter under prescribed load conditions by measuring the diameter of the indentation. Now we have also the calculation of HAZ, DOP and BW. So for calculation of heat affected zone, depth of penetration and bid width, we applied chemical, that is nitrile solution, 98% ethyl alcohol and 2% nitric acid. For the test, we need to make test specimen surface very smooth using different emery papers. After making the surface smooth, we washed it very well. After washing, we applied nitrile solutions. After a few seconds, we got black spot for welded zone and light brown spot for heat affected zone. We marked the bid width, heat affected zone and depth of penetration. Using microscope, we measured HAZ, BW and DOP. When the heat created by welding process applied on the material, it melts the material and again freezes due to heat dissipation. The depth up to which material melts is called depth of penetration. After melted zone, heat affects the material up to much more depth but could not make it melt. This depth after depth of penetration is called heat affected zone. The width which gets melted is called welded bid width. And coming to the impact test, there is a Charpy test. It is usually done for impact strength or toughness of a material. In this test, loads are that are suddenly obtained to a structure are known as impact loads. Impact tests are performed to assess the shock absorbing capabilities of the materials like rupture energy, modeling of rupture, notch impact strength, etc. So the principle employed in all impact testing procedure is that the material absorbs a certain amount of energy before it breaks. The quantity of energy that's absorbed is a characteristic of physical nature of the material. If is brittle, it breaks more rapidly, and for tougher materials, more energy is required to get fractured. Now, if we consider this comparative study, here you will find that when the travel speed is 2.1, wear feed speed is 42. When the travel speed is 4.2, the wear feed speed is 85. And when the travel speed is 8.5, the wear feed speed is 169. And when the travel speed is 10.6, the wear feed speed is 212, such that the travel speed given is in millimeter per second, while the wear feed speed is given in also millimeter per second. Now the constant parameters are wear type or diameter. Here we are using ER70S6 oblique 0.045 inches, that is 1.2 millimeter. Shielding gas is 90% argon and 10% CO2. Shielding gas flow rate is 40 feet cube per hour. Travel angle is 0 degree and work angle is 0 degree. Arc length is 0.13 inches, that is 3.2 millimeter. And contact tip to work distance is 0.75 inches, that is 19 millimeter. So here is the comparative study of the different parameters using that is being affected the welding. So you can see with the increase in travel speed, the wear feed speed is also increased. So these are the important parameters we need to know while going through a welding process. And the different parameters that affect this welding has a great consequences on the strength as well as the retention power of the welding bid so far joint. Now this contour Now we have got some other parameters, welding parameters. Others are as follows also. We have this contour, quasi simultaneous, and the required laser power is 20 to 100 watt for contour, and for quasi simultaneous is 100 to 400 watt, and simultaneous is 50 watt to kilowatt. Now mechanical access needed is yes in contour, no in quasi simultaneous, and no in simultaneous. Closed loop process control required is yes, and quasi simultaneous is limited, and simultaneous is no. Set path measuring contour is no, and quasi simultaneous is yes, and simultaneous is yes. Flexibility is plus for contour. Uh, and double plus for quasi simultaneous, and simultaneous it is 0. So see, we have discussed today the different parameters. In the next class we will continue this class to discussing more parameters as well. So thank you for watching.